My name is Emily Diana, and I am a third-year statistics PhD student at the Wharton School at the University of Pennsylvania. I'm very pleased to be with you today to talk about some recent work from my research group. This is work with Michael Kearns, Seth Neal, and Aaron Roth, and we are looking at optimal, truthful, and private securities lending. So in this talk, I will give an overview of the problem. I will talk about some of the different settings that we analyze: a non-private setting, a private setting, and a more kind of general real-world setup. And throughout, I will talk about these issues of privacy and truthfulness and optimality. And before I dive into the problem, again, I want to mention that this is work with Professors Michael Kearns and Aaron Roth in computer science at the University of Pennsylvania, as well as Seth Neal, who recently graduated from our program in Wharton Statistics, and he is now an assistant professor at Harvard. This work is accepted at the 2020 ACML International Conference on AI and Finance. You can find the paper on arXiv, and you can also reach out to me with questions at ediana@wharton.upenn.edu. So without further ado, we were motivated by challenges associated with securities lending, the mechanism underlying short selling of stocks in financial markets. So we are considering a situation in which a lender wants to allocate a scarce commodity. So for example, they may have a certain number of shares of stock that they can lend. And in particular, this is a setting in which privacy concerns or demand uncertainty may be in conflict with truthful reporting. So the clients, the people who want the stocks, may be unwilling to tell the lender exactly what they want for various reasons. It may be because they believe that by lying they can actually get more shares. It may be because they don't want other people to know about their motives, about their beliefs. For example, we were thinking of the situation in which a large buyer may request many shares of many different types of stocks while only intending to actually short one of those types. And by asking for all of these extra unused shares, they're masking their true motives, their true desires. So our goal here is to construct a privacy-protecting allocation mechanism that motivates truthful reporting without sacrificing too much utility. So we wanted to find a way that the client and the lender could kind of act together in a way that's beneficial for everybody, in which clients are motivated to tell the truth, so request as many stocks as they intend to use, and in which they can also eventually be guaranteed that they're not losing too much privacy. And as an example, we can consider this situation on the left here. We have a lender and we have a potential client. The client may only want to use 1,000 units of the stock, but in order to mask their true intent, they are way over requesting at 100 million shares. So this is potentially very wasteful, and we would like to find a way for them to actually request those 1,000 shares that they intend to use. Also, because in general, we imagine that the lender is making money off of the number of shares that are actually shorted. So if they lend a share to a client, but the client never goes and sells that share, then we imagine that the lender is losing out on money. So they want to make sure that people actually use the stocks that are lent. So this is our general setting, and I will go into a few different scenarios, but this is the goal. So more technically, we are imagining that there's a lender who is distributing up to V shares of a certain stock to N clients over a time horizon T, and this is at a fixed price per unit. So this is because often in mechanism design, prices are used as a tool to enforce truthfulness. So prices are used as a way to dissuade clients from way over requesting. But in our case, we wanted to think about how we could encourage clients to be truthful without having to adjust price. It makes things simpler, it makes them more consistent, etc. So we imagine that every client has a non-strategic distribution over usages. We'll call this UIT. That is for a distribution over usages for client I at time t. And we say that it is non-strategic because we imagine that the client is kind of given this demand from an external source, so they don't have control over what they need. Now, what they do have control over is their strategic response. So a client can choose what types of requests they make. So once they find out that they need a certain number of stocks, then they can decide to over-request, they can decide to under-request if they want to, they can decide to request as many stocks as they need. This is their distribution over requests. Together, we can combine these to form a tabular joint distribution of usages and requests for any client at any time. And only the request is ever visible to the lender. So the usage is a latent variable that the lender can get some censored information on later, but they're never really sure. And we imagine that the client's payoff is the number of shares the client actually uses. So it'll be the minimum of what they request and what they intend to use. So if they are granted more than they tend to use, then it'll be their usage. If they are granted less than they wanted to use, then it'll be the number they were granted. Now, we consider a distribution for a client I at time t truthful if this conditional distributions of requests giving usage only has probability 1 if they are requesting as many stocks as they intend to use. So basically, they always request exactly as many stocks as they intend to use. They never deviate. So here are two examples of strategic distributions for a certain client. We have a truthful distribution on the left and an untruthful distribution on the right. You'll notice that the truthful distribution has a diagonal structure where requests and usages always match, and the untruthful distribution has some off-diagonal entries. And these off-diagonal entries will end up confusing the lender and make it harder for the lender to know what the client wants. And up here, I am just demonstrating that this usage distribution for the clients, in this case, is uniform over using 0 shares, using 1 share, or using 2 shares. So the sum of the horizontal entries are all 1/3. There's an equal probability that they might need 0, 1, or 2 shares at this time. Now, the lender's goal is to choose an allocation rule A that maximizes his or her utility. And the way we define an allocation rule is that an allocation rule A is a one-shot algorithm that maps a set of requests by clients and their conditional distributions of requests given usages onto an allocation ST. So the lender has V units of a stock, of a good. They want to allocate those V units among their end clients. So the sum of these individual allocations has to be less than or equal to V. And for the rest of this section, I will drop the subscript T because this allocation rule is a one-shot algorithm. It's occurring just at one time. And importantly, it assumes full knowledge of the conditional distributions Qi of Ri given Ui. And this can be estimated from a client's history. And I will come back to this at the end of the talk. But until then, we're assuming that the lender is able to have knowledge of these distributions, or at least a very good guess. Now, the utility that the lender gets from an allocation rule A is the basically the sum of the expected number of shares that are actually used. So it's the sum over all clients of the minimum of the number of shares given to that client and the probabilistic usage of that client. Finally, the utility for the client is the number of shares that he or she uses, so it's the expected number. It's the expectation kind of over this allocation rule of the minimum of the number of shares given to the client and the used number. Okay. So the lender does have to do a little bit of work to try to figure out the this latent variable u. So again, the lender gets a request vector from the clients, and based on the history of the clients, they can make kind of probabilistic inferences about how many shares each client may intend to use. They can calculate a posterior on u given r with Bayes' rule, and then they can calculate tail probabilities. And what I mean by a tail probability is the probability that a client will use S or more shares. So it's not just will this client use 1 share, will this client use 2 shares, will this client use 3 shares, it's will this client actually use 1 or more shares. And this is useful because the way that we recommend that the lender allocate shares in this setting is through a greedy approach, where each time they just look at which client is most likely to use an additional share, and then they allocate that additional share to that client. And this is the allocation rule that I show here. So this algorithm operates by sequentially assigning shares 1 through v, where each share is assigned to the client I most likely to utilize 1 additional share. This is pseudocode for our allocation rule. The lender knows the maximum number of shares he or she can allocate. They know the number of clients requesting shares. They have these tabular posteriors, and they have request vectors from the clients. In the end, they will output a feasible allocation. And again, they do this by, for each share, 1 through v, figuring out which client has the highest probability of using an additional share, and then giving that client that additional share. It turns out that this algorithm provably maximizes the expected payoff for the lender, and that the lender can do no better in expectation by using any other allocation mechanism under these assumptions. So if the lender chooses to give all clients the same number of shares, for example, that is not going to be better than this greedy approach. If they give everybody the same proportion of the number of requested shares, it's not going to beat this approach in expectation. And this encourages clients to be truthful. So given that the lender is solving the allocation problem optimally for the reported Q distributions, it turns out that truth-telling is a dominant strategy for clients. What this means is that regardless of what anyone else does, it is in a client's best interest to tell the truth. This is our formal statement of the theorem. You can look in the paper for kind of more discussion of this proof and a proof, but I will kind of outline what the technicalities are saying. So this minus I notation is talking about the strategies and the requests for all of their clients. So no matter what anyone else does, it is best for the client to be truthful, in that each client maximizes their own payoff by adopting a truthful strategy. And this is because when a client is truthful, it gives the lender more information, and the lender can make better decisions when allocating the stocks. So if you recall this idea of tail probabilities, if a client is truthful, all of the tail probabilities will be 0 or 1. So the lender knows 100% whether the client will use each additional stock. So here, let's go back to our example of a truthful client and an untruthful client. Our truthful client has this diagonal structure where the untruthful client has an off-diagonal structure. So let's imagine that the lender only has one share to allocate and both clients request one share. Who gets the share? So using the algorithm that I outlined, the lender needs to know the tail probabilities. They see that if each client requests one share, then they'll certainly use 0. That's trivial. But the probability that client I uses one share, given that he or she requests 1, is exactly 1. If you look at this column here, then when RIT equals 1, the only option for UIT is 1. But when you look at client J, if RJT equals 1, there are more than one option for UJT. Client J could use 0 stocks with 1/3 probability, or they could use 1 stock with 2/3 probability. So the lender, wanting to maximize the chance that that stock is actually used, is going to allocate it to the truthful client, client I. And here's a graphical representation of that. This is graphing those tail probabilities that I just showed. So trivially, 0 stocks will be used by both clients, but if they request 1, then client I will certainly use that additional stock. Client J only has a 2/3 chance of using it, so as a lender we give it to client I. So these are very strong results in a non-private setting. But part of the motivation for looking at this problem is to figure out ways in which we can incorporate privacy. So we don't want clients to have to lie in order to protect their information. So the way that we do this is by reformulating the problem as an auction, as an ascending price. We reformulate the algorithm as an ascending price auction, and then we are able to take that and incorporate privacy by adding noise at different levels of the algorithm. So I will outline kind of the changes and assumptions that happen here and what that ascending auction looks like. And then I will talk about what guarantees we get. So this will still motivate clients to be truthful, and it will still have a very good payoff. So again, this is a setting in which clients have distinct privacy concerns. And then later on, I will also talk about kind of adaptive strategies, but I'll wait for a bit. So as I said, we reconceptualize the problem of computing the optimal allocation for the lender, given known distributions for clients, as computing a social welfare maximizing allocation with respect to a set of valuation functions for each client I. We then give an algorithm that uses an ascending price auction formulation to compute an approximately optimal allocation, which can be adapted to satisfy joint differential privacy. We then, so in this auction, we are considering a more general setting in which there are V identical units of a good that are being sold to N bidders. Each bidder has an arbitrary decreasing marginal valuation function for up to U units of each good. And our goal is to find the welfare maximizing allocation. I want to note that we are able to map our previous algorithm onto this one by making explicit the valuation function for each client. So here, for an agent I who requests RI shares and has a posterior demand distribution, QI of UI given RI, we define the valuation function for agent I as a function of the quality of the good that they receive. So we say that VI, the valuation function for client I, if they receive S units of good, is 1 over, like this, is 1 over the maximum units of good that they could possibly request or possibly use, times the expectation of the minimum of how much they were given and how much they wanted. So this is similar to what we were seeing before, where what they really care about is the minimum of their allocation and their intended usage. And given an allocation S of V shares to N clients, we define the total social welfare to be the average of all of these valuation functions. So we formulate this as an ascending price auction. So you can imagine a bunch of bidders or clients sitting in a circle or just sequentially making a decision about whether they want to make a bid on a good. And they decide whether they want to make a bid based on whether the marginal utility for an additional unit of the good is greater than the price. So we increment the price by alpha after every V bids. So this is another parameter to our algorithm. It determines the speed of the auction as well as the accuracy. And the auction terminates when there are no more bids. So here is the pseudocode for this algorithm. We see that we have this kind of speed and accuracy parameter alpha. We have the number of clients. We have all of their valuation functions. The maximum number of goods that they could ever request or want to use, and the number of goods that the lender can allocate. Again, the lender will allocate a feasible allocation S so that they give out less than or equal to V units of good. And the main procedure works in this way. We start the price at 0. And we go through and we let every client decide if they would like to bid, if they would like to kind of claim that unit. So each client calculates their marginal utility for an additional unit of the good, and this needs to be decreasing, so the utilities either stay kind of consistent up until capital U, or they actually decrease. And if their utility is greater than the current price, then they will make a bid. So we increase the bid counter. We give that unit of good to that client, and maybe they take it from someone else. So these units are kind of being passed around. It's not quite the same as before, where as soon as the unit is allocated, we can never go back. Here we are kind of making changes. And then once all the goods have been handed off, so once there have been V bids, we increase the price and we do it again until no one else will make a bid. So this algorithm will, kind of how quickly this algorithm goes is related to alpha. So for smaller alpha, smaller price increments, this algorithm will go for longer. For a more coarse price increment, this algorithm will terminate earlier. And at termination, we have a near optimal allocation, again determined by alpha. Okay. And this is leading up to the ability to add some noise to make this auction private. And I want to make very specific what I mean by private. So we're talking about the notion of joint differential privacy. We say that a mechanism A is jointly differentially private if for every entry I and every pair of data sets that differ just in that entry I, the output on all of the other data points can't look that different depending on whether like I was in that data set or was changed. So let me clarify that a little bit. Here, xn is a data set domain, so it's a data set consisting of n entries. And on is the set of kind of outputs on each entry, so the output of the algorithm. We say that two data sets are I neighboring if they differ in only the report of agent I, so that information could change. And what we're looking at here is kind of how much the allocation of the algorithm changes depending on a change in agent I's report. So intuitively, this prevents adversaries from learning too much about agent I by observing the allocation to agents other than I. So the agents So everyone except for agent I cannot kind of collude and pool their information and learn too much about agent I's behavior. So in order to make the previous algorithm jointly differentially private, we make three main changes. We have to inject noise in a systematic way in order for the kind of n-1 agents not to be able to discern too much about that extra agent's behavior. So the running count of total bids placed so far is computed privately. So we use a differentially private estimator, and because the price at each round is computed as a function of the bids placed so far, remember that we increase the price after every V bids, the price trajectory ends up being differentially private as well. Secondly, rather than terminating exactly when there are no more bids placed, we allow the algorithm to terminate a bit early. So we have a parameter rho that kind of determines accuracy of the algorithm, and it gives us an early stopping rule. So this limits the maximum number of times that any single buyer can place a bid, and it allows us to bound the error of the differentially private bid count. Then rather than running the auction with a supply of V shares, we run the auction with a supply of V minus E shares, where E corresponds to the maximum error of our differentially private bid counter. And this ensures that our computed allocation, which now may over or under allocate with respect to its target supply, is always feasible. So we add a little bit of noise to how many shares were allocated in the end. So we added noise to the number of bids placed to the bid counter, which made the price private. We allowed the algorithm to stop a little bit early and to not necessarily allocate all shares. So with this information, bidders cannot collude to figure out what one person was doing. So this obtains kind of in this theme of wanting high quality private mechanisms. This works well for sufficiently large auctions when we have lots of people relative to the number of goods that can be allocated, and for an appropriate choice of the privacy parameter epsilon. We can achieve joint differential privacy while still outputting near optimal welfare. So we're still doing about the best we can do in terms of making sure that as many stocks are used as possible. And because of the privacy, it is still beneficial for clients to act truthfully. And what I mean by approximately dominant strategy truthful is that for the vast majority of clients, it is in their best interest to act truthfully. And the last thing that I want to discuss here is that so far we have been making assumptions that we kind of have full information about either these request distributions for clients, so you will call the QI of RI given UI from earlier, or utility functions. We assume that the lender kind of knows how clients will behave probabilistically. But that's that's a strong assumption. That's not something that we really have in real life, and we would expect clients to adapt their strategies. So the last thing that we do in this paper is we generalize these results to an allocation mechanism that actually takes into account the history of clients and uses the history as well as the current requests to make near optimal private allocations. So an allocation mechanism, it is similar to an allocation rule, except that this is no longer a one-shot deal. This is going over multiple time steps, and it is incorporating history. So it maps requests at time t in a history over clients to decide how to allocate the shares. So now each client I has the freedom to adaptively choose an arbitrary mapping that maps a realized history and demand, HT and UIT, to a request RIT. So in the allocation rule that I mentioned before, knowledge of these QIs, these conditional distributions of request giving usages, were baked into the definition that we used. Here, that's not the case. This is a more general framework where clients can have a changing strategy. We define the utility of a client I very similarly. Basically, the difference is that now we're considering over the long run, what is the expected number of shares that the client gets to use compared to what they wanted. And the lender is kind of summing over all this time, so 1 through T, how many shares are actually used. So how many of those shares that the lender lent out are getting shorted and used. And like I said, we're imagining there's a fixed price on these shares, so we can kind of think that the lender is making money whenever a share is shorted. And this is pseudocode for the allocation mechanism. You'll notice that this is similar to what I was talking about before. So we have a procedure, an allocation mechanism that takes in utilities of clients. It knows how many clients there are. We know how many shares we have to allocate. We know how many rounds we can allocate over. And we have a private auction with appropriate parameters epsilon and alpha. So over every time step, 1 through T, we go through all the clients, 1 through N, and each client will draw a usage. So recall that these usages are not strategic. It's just client I at time T decides I need this many shares, I need them. And they get to choose whatever request distribution they want, and then they draw a request. Now the lender sees those requests and it updates its running estimate of how that client is behaving. So we are going to be using the assumption that the lender is always a bit forgiving. So they always assume that maybe now the client is going to act truthfully. But they remember that if the client was lying before, they kind of do a weighted update. So using this information, using this weighted update on the client strategies, the lender computes an allocation using an auction. So they run an auction at every round. They output the shares, and then they observe how many shares were actually used. And they use this knowledge to update those distributions. So if I gave client I the benefit of the doubt as a lender, and then client I lied to me, then I get to use that information in the next round. And we do this iteratively over T rounds, capital T rounds. Our mechanism again enforces truthfulness as an approximately dominant strategy and guarantees near optimality. So this is a lengthy result. Again, you can look in the paper for more detail, but essentially what this is saying is that if we have a private auction and we have appropriate privacy and accuracy parameters, then for a 1 minus b fraction of the clients, they are best off being truthful. By being truthful, they are kind of most likely to do well, and the lender will also get very close to optimal utility by using this algorithm. So in summary, without privacy constraints, we construct an optimal greedy allocation for which truthfulness is purely a dominant strategy. In order to guarantee clients an appropriate notion of privacy, we then reformulate the allocation rule as an ascending price auction in which clients cannot collude to infer too much information about any one bidder. And finally, we expand this into an allocation mechanism that can handle arbitrary and adaptive client request strategies while still providing privacy and near optimality and incentivizing truthfulness. So again, thank you very much for having me here. Feel free to contact me with questions, look at our paper online, and we welcome any feedback. Thank you.